Okay, no one has joined. Let's wait for 5 minutes. It's recording. Okay. So let's begin. Welcome everyone. Welcome to week 4 live interaction session for the Matlab course. This course is Matlab based programming lab in chemical engineering. Okay, so the weekly classes that I do, this doubt solving session or live interaction sessions, are to assist you with the course which is run by Professor Parag Deshpande. Right. So little brief about me. I'm Bhavesh Moorjani. I have completed my graduations from MS University, Vadodara. After that, I was working at Gujarat State Fertilizer for a while, and then I joined Ph.D. at IIT Bombay. During my undergraduate, I have been using Matlab. I was introduced to Matlab in my undergraduate, and then for my current research work in my PhD work, I use Matlab here and there. And in this course, I am your TA to help you to get used to with Matlab, so that you can solve various chemical engineering problems in Matlab, right? So these are various social sites where you can contact me if you want, right? So let's begin with the today's lecture. Now, before beginning with the today's lecture, although there is no one here, let me put a message. If there happens to be connectivity issue in between, please wait for. This is just because right now I have internet connectivity issue, so I'm using my mobile data, and since it's raining, so I'm not sure about the electricity connection and all. So if there is any connectivity issue, uh, you should wait. I will join. This is just for an online audience. If somebody joins right now, for those of you who are watching in YouTube, I think it's fine. Okay. So in the first two lectures, what we saw was we got introduced to the Matlab. We learned about why we need to do modeling and simulation of various chemical engineering processes, and what programming languages are available to do this modeling, right? And out of which we selected Matlab, and with Matlab, the second week was followed by the introduction to the Matlab, and from the week third we started various problems in the Matlab, like solving various chemical engineering problems in the Matlab. So last to last week, which is week 3 for you, was about doing problem solving about friction losses in pipe. And in the last week, sir has taught about problem of CSTR, or a mixed flow reactor, how to find the temperature concentration profile in CSTR, and how various parameter affects that, right? So this is the lecture note from sir's class. So what actually sir has taught in the class was that if you have a problem of CSTR where which is jacketed, and it's a cooling or a heat it's a cooling jacket, and there is a reaction occurring in the CSTR. So you have a mass balance equation, you have a heat balance equation, and these two equations you have to solve simultaneously to find the concentration and temperature profile in the CSTR, right? So you have been given various parameters about the CSTR, different cases, and then based on that cases you had to find how the initial concentration and temperature in the reactor changes. The effect of initial concentration and temperature in the steady state values of the reactor. Okay, so steady state value meaning you have to find Ca and temperature value in between, right? Then you had to examine the feed temperature and jacket temperature on the concentration and temperature of the reactor. So which was again extension of problem statement 1, where you had to look at various values and see how they affect the how they affect your reactor parameters, right? Sir has already given the not exact code, but the pseudo codes and some of the MATLAB codes are already given. So I hope you all are able to implement this code in your own MATLAB and are able to get the solutions. If you have any specific doubt related to this problem, do let me know. I'm not going to solve this particular problem step by step because I think sir has spent enough time onto this part, and it's fairly straightforward. Uh, but if you still have any doubt and you want me to solve this, do let me know, either if somebody is joining right now, or if you are watching it on YouTube and you want me to solve, you can let me know over there also, so that I can plan it for the next lectures, right? This was again fairly straightforward question. Now here the solution to this heat and mass balance required use of inbuilt solver to find the temperature and concentration values, right? So we used fsolve here to find that solution, and based on that the various profiles were generated. So this was what sir has taught. So what I will do, instead of CSTR, I have prepared a problem for plug flow reactor, so which is kind of following the similar aspect of CSTR problem, where we have been given information about plug flow reactor, various reactor conditions, and then you have to find the concentration and temperature profile inside the plug flow reactor, right? So the only change will be the type of equation that we use to represent our plug flow reactor compared to CSTR, and how we will solve this plug flow reactors, right? Now in the week 3 third week's content, sorry, in the fourth week contents, which was studying the CSTR reaction in the CSTR, the main solver or main inbuilt function that we relied from the MATLAB was fsolver, where you had to solve the mass balance and energy balance equations to find the values which satisfied your fundamental equation of CSTR, right? Similarly, similarly here right now we will use inbuilt function according to the PFR equation. Okay, now in the CSTR part, main use was only fsolver, since there were non-linear equations, and we had in the previous lecture also seen various command related to solving this non-linear equation, right? So if you recall, in the last lecture we studied these 4 basic solvers which are used to find the solution to non-linear equation. You have f0 command, you have fsolve command, vpa solve, and solve. Now the basic difference between all 4 has been listed here. So if you have a single variable function, single variable equation, non-linear equation, then using f0 is a good idea, which works on the univariant optimization problem. So it uses the combination of bisection or secant method to find the solution. If you recall, in the last lecture we also studied about the how to code our own bisection method, and then we compared our result with the f0 inbuilt functions also. Then if you have a multi-variable multi-equation problem, then using fsolver is a good idea. In both f0 and fsolver you have to provide some initial guess in order for a solver to work. Fsolver uses this trust region method or Marquardt algorithm. These are nothing but an optimization method. So if you will study some optimization course, you will get to know about this method more. Right now we don't have to worry about it. You can get some basic idea about this method if you are interested. You can even try to code it also, and then compare your result with the inbuilt function, just like what we did with the bisection method. Then next we have VPA solve. In VPA solve, it was that we provide us symbolic equations and it will provide us the numerical solution, right? It does not require any initial guess. We can provide some bound in between which we want to work. Okay, so it works with symbolic equations and gives us the numerical result. But if we want our solution as also form of the symbol, then we can use the solve command, where we provide input equations in form of the symbols, and then it also gives us the result in form of the symbols, right? Apart from this, we also studied root and roots command, which are used to find the solution to polynomials. Okay, polynomial roots can be found with the help of root or roots command. Okay. Now I have prepared some of these problems, like some of the questions which are again related to the solver, since the uh, again main idea in the CSTR problem was to use solvers, and apart from that the plotting was another aspect, right? So there are this I think 11 problems I have prepared, but before going to that I would like to move forward with the plug flow reactor example, which is the main aspect. We will code this problem. So this, if you haven't solved CSTR problem, it will help you to understand CSTR problem analogy, and then probably if you want to code and compare your result with the source result, you can do that, right? So we will start with the plug flow reactor. This will be the main content of today's class, and then after that we will move forward with the solving the sub problems where with the help of various inbuilt solvers, right? So in the plug flow reactor, what has been given to us is that we need to design a plug flow reactor for some liquid phase second order reaction, A giving B product, right? Where the reaction rate is K into Ca to the power 2. That means it's a second order reaction. Reaction is exothermic. Heat of reaction is also given as minus 50 kilojoule per mole. Now reactor is operating adiabatically, so no heat exchange will happen. So you can consider it's an insulated reactor. Now based on the reactant parameter, we have been asked to study the following. First part is to find the basic solution, which is that we have to write a Matlab code to observe the change in concentration and the reactor outlet temperature, as well as the conversion with the variation in reactor volume. So now in plug flow reactor, as you know, either you consider the volume of the reactor or the length of the reactor. So if you recall your basic reaction engineering principle, CSTR is called as a perfectly mixed reactor, while plug flow with the change in the length of the plug flow, you go from initial concentration, your reaction occurs, and your concentration changes with the length of your reactor, right? So with the length, your concentration profile will change. So if you assume the constant area of constant cross-sectional area of this plug flow reactor, and as you move forward from the inlet to the outlet part, with the change in the length, your concentration will change. So here, instead of concentration, what we have been asked is like to study the change in the concentration with respect to volume. Instead of length, we have been asked to study the concentration change with respect to volume. So you can consider it in other sense that maybe cross-sectional area is constant, but instead of providing length, they are asking us to study the overall volume. But let's say if cross-sectional area is same, if I increase the length, this is my sum volume. Further increasing length, I will get a higher volume. So on. So same analogy you can apply here. But whatever our equation here will be, they will be coded in terms of the volume rather than the length, right? So with the change, so we know that in the plug flow reactor, with the change in the length, as you move forward from inlet to outlet, your concentration profile will change. Now since this is an adiabatic reactor, so based on the endothermicity or exothermicity of your reaction, temperature inside your reactor will also change as you move forward from inlet to outlet, right? So here the reaction is exothermic, and since the reactor is adiabatic, it's insulated. That means your temperature inside the reactor will increase from inlet to outlet as conversion happens. So we have to find what exactly this conversion is. Is it decreasing parabolically? Is it decreasing exponentially? How temperature is changing with the reactor volume, right? So this is the first aspect that we have been asked to study. Then second aspect is we have to do sensitivity analysis, where we have to study the feed concentration effect. So we have been given various feed concentration, initial concentration at the inlet, and we have to plot final conversion. What is this initial concentration and outlet temperature with respect to initial concentration. Another problem, subset of problem 2 is we have to study the inlet temperature effect T0. So T0 variation is also given from 300 to 340 Kelvin at a given inlet concentration, and we have to again plot same conversion versus inlet temperature and outlet temperature versus uh, inlet temperature, right? And third is we have to find an optimal condition, so that is determine the inlet temperature that maximizes the conversion while keeping the outlet temperature below 350 Kelvin, which is which is determined based on some safety constraint, right? This example is obviously hypothetical, so some of the parameters are selected just to illustrate how various values will change if you tweak, let's say, initial concentration, if you tweak the volumetric flow rate, right? But you can consider some real world example. You can find your reaction engineering books, take out the data from that, or if you have some access to industry, and if you can take out the real time data from that industry, and then you can study same system in the Matlab. So you have the actual data from industry or from some reference, and then you can see how various values affects your overall design of your reactor, right? Right now it's an hypothetical case, so the values are arbitrary, but same problems with the same idea, you can use the real world example and see what changes you can find. Okay. We have been given reactor parameters. So what are these parameters? Initial concentration, which is inlet concentration, inlet temperature of the feed, volumetric flow rate is given, reactor volume is given, we have activation energy for the reaction, pre-exponential vector, heat capacity, density, and the gas constant, right? Okay, so this information has been given. Now if you recall, the strategy that follows, first is you have to identify what your problem is, right? Then second problem is you have to numerically define how to represent your system with how you can represent your system with the mathematical equations, and you have to identify what kind of mathematical equations you have in your system. Once you do that, you will be then you have to identify the methods by which you can solve this mathematical equations, what numerical method or analytical method you can apply to solve this equation, and then accordingly you model your system and then finally simulate it, right? So first problem, we understand what this plug flow reactor questions is trying to say, that we have been given some parameter for plug flow reactors, and then we have to study the change in the concentration and temperature profile for this plug flow reactor with the change in the volume, right? So this first idea is clear to us. I'm talking about part 1, we will solve part 2 and part 3 also. So now let's try to first model this reactor, okay? So if you will recall, I'm not going into the detailed derivations, but if you do the basic mass balance and energy balance for this plug flow reactor, right? So this is how these are the what governing equation you will come across, right? So you have change in the concentration of your component A with volume. It will be nothing but equal to minus rate of reaction divided by volumetric flow rate, right? So this is basic mass balance equation, right? Inlet minus outlet plus generation minus disappearance is equal to accumulation. There is no accumulation, so that term is 0. There is no generation. Disappearance term is that's why minus R rate, and then inlet and outlet you have, right? So based on that, if you simplify it, you will come to this part, and your rate of reaction. So it has been given that this rate of reaction follows the second order part, right? So you have minus R is equal to K Ca square. So this is your mass balance equation, right? Now if you will see this equation, this is a differential equation. More specifically, it's an ordinary differential equation of first order, right? Then on the energy balance part, if I consider the delta V volume of my plug flow reactor and try to try to do the energy balance for that particular part, what you will get is change in the temperature for that particular volume is equivalent to minus heat of reaction into rate of reaction divided by rho Cp V0. Again, it's an energy balance part, so just do pen and paper calculation, you will come to this. If you have any doubt, reach out to me, I will do the detailed calculations, right? Okay, now here also in the dt by dv energy balance equation, we know the uh, change in temperature with respect to volume, but here we have a rate term which also includes temperature. So okay, uh, and so rate term is k into Ca square, so rate includes temperature also, it also includes Ca. Similarly, in the dc by dv part, you have k. K is represented as k Arrhenius through Arrhenius equation, k exponential k into exponential of minus Ea by RT. So it also includes temperature. So these are coupled coupled ordinary differential equation. Why coupled? Because both the variables, temperature as well as concentration, are part of the both equations, right? So they are interconnected. So that's why these are coupled equations, coupled ordinary differential equations. So while solving the plug flow reactor, what we identified is that we have ordinary differential equations for mass balance and energy balance. These are first order differential equations, right? Then we also identified that this both equations are coupled. Coupled in the sense that the energy balance includes both temperature and concentration term. Similarly, mass balance also includes both concentration and the temperature term. Okay. Now we have to identify what kind of numerical methods we can use to solve this ordinary differential equation. Now, since we are using Matlab, which has this inbuilt library of various functions, inbuilt library of various numerical methods available through inbuilt commands, so we don't have to worry about solving the problems from the scratch, but we have to identify appropriate method by which I can solve these equations, right? Now if you don't worry about how exactly to solve this problem, by just looking at the left hand side of equations, what I can see that I have dCA by dV, which denotes change in the concentration of A with respect to volume. From energy balance, I have dt by dV, which denotes change in the temperature with respect to volume, right? And what we have been asked in part 1, that we have to write a Matlab code which observes the change in concentration and the reactor outlet temperature with the and conversion also with respect to reactor volume. So these two equations are sufficient. If I integrate this from, let's say, 0 to given volume of reactor V, then I will be able to find what is the concentration. Similarly, if I integrate this equation, then I will be able to find what will be the temperature at the reactor outlet, right? So this both equations are sufficient enough to solve our problem, but now we have to identify what method to use. Here we have been given hint that we should use ODE45 function in Matlab to find this solution, but we will come to that part also. Let's say we don't know, like you, I also start with the very basic, that I don't know which command to use to solve these problems, right? So what I will do, we will take the help from Matlab itself. We will search what are the functions in Matlab to solve this ordinary differential equations, and then based on that, based on the available options, we will select the appropriate options which best fits our case. Okay. So here, what I will do, I will go to the Matlab documentation and I will search. Since I know my system has coupled ordinary differential equation, I will search coupled OD. Okay. I am starting very fresh, like you. I am also thinking that I don't know what kind of solver to use, right? So this is how we will approach. It's showing me various options to sorry. For coupled OD, it's giving me this two results. So first is choose an ODE solver, right? So this seems like an appropriate starting point, since I don't know what kind of solvers are present in Matlab to solve this ordinary differential equations, right? So ordinary differential equations which contains one or more derivatives of dependent variables, which is y. So let's say y is a dependent variable with respect to single independent variable t. Okay, then here I mean obviously it describes various types of ODE. So here types of ordinary differential equation are discussed. One is explicit, which is that your differential is a function of both dependent and independent variable, right? Now there are other also linear implicit ordinary differential equation, which value is given, like which equation form is given to us. Then you have fully implicit. So right now if you look at this equation, the mass balance equation, right? So here what I can see is left hand side represents my derivative, on the right hand side I have concentration. So if I consider C as y, volume as t, so my right hand side contains the y value also. So it's an implicit equation, right? So sorry, it's an explicit ordinary differential equation. So because explicit ODE is where derivative is function of both the dependent as well as independent variable, right? Similarly, for energy balance equation, my derivative is function of R, which includes temperature, right, and as well as the concentration, which includes temperature as well as the concentration. So again it's an explicit ODE, right? So I have identified, okay, my system is an explicit ODE. Now let's look what Matlab suggests to solve, to which method to use to solve this kind of ODE, right? So if you will scroll down, and here basic solver selection is given, right? So first solver is ODE 40, okay, and its accuracy is medium, and here you have a column which says when to use this ODE. So most of the time ODE 45 should be the first solver you try, okay. It doesn't provide much information why, but let's look at the ODE 45. So if you go here, what it says that ODE 45 solves a non-stiff differential equation with a medium order method. Right now I don't know what this method is. If you will search through Matlab manuals, you will find what exact method they are using, if you are interested, right? So here the description is given as so this is how you use ODE 45. You provide ordinary differential function t span and y0, where t span is your limit, your integral limit for your independent variable, right? So it goes from t0 to tf. So this ODE 45 integrates the system of differential equation from t0 to 2f with initial condition provided as y0, okay. Each row in the solution array y corresponds to the value written in the column vector t, okay. So each row in the solution array y corresponds to the value written in the column vector t. So what it will do, from t0 to tf, it will vary the value of t from t0 to tf based on the initial condition. It will integrate your ordinary differential equation and provide the corresponding value of y, right? So if you will see, that's what exactly we want, right? We want to see the change in the concentration and temperature with respect to volume. So from at the start point of my reactor, at the inlet of my reactor, my volume is 0. Since as I move forward, my volume is changing, right? So I want to observe what is the change as I move ahead in the reactor, so as my volume is increasing. So basically I want to integrate with respect to V. I have initial conditions with my which is initial condition, which is your inlet concentration Ca0, your inlet feed temperature T0, right? So this fits my description, that this fits my requirement, right? So this based on this description alone, I can assume that okay, this ODE 45 inbuilt command is probably useful for for my need as of now, right? There are some examples also given, that let's say you have this equation dy by dt is equal to 2 times t. Your span of variation of t is also given 0 to 5. Your initial value is also given, y0 is 0. For t equal to 0, your y0 is 0, right? Then you use your ODE 45 equation in this manner, and then you get the value of y for value of y for various value of t, right? So this is how your solution will look like. Okay, so based on this description, I am able to decipher, okay, maybe this isn't good option. You can also check what are the other options, right? So then there is, you have OD 23. It can be more efficient than OD 45 at problems with crude tolerance or in the presence of moderate stiffness. Okay. So let's look at the OD 23 part. So OD 23 also integrates the system of differential equation y dash is equal to fty from t0 to 2f with initial condition provided y0. Okay, and each row in the solution corresponds to each row in the solution of solution array y corresponds to the independent variable column vector t. Okay, so this also description is similar to what we have seen in this part. Now only difference I think is what kind of method they use in the background to solve this problem. Okay, now the description of both ODE 45 and 23, it shows that it talks about the stiffness of the ordinary differential equation. Right now the ordinary differential equations that we are using are moderately stiff. I mean, we don't have to worry about such terminology as of now. We can consider them to be simple equation, and I think OD 45 could be a good starting point. If you have a more complex ordinary differential equation, then you can look into the behavior of your ordinary differential equation. So there are various parameters which defines the stiffness of your differential equations, right? You can further categorize them. In that case, based on that categorization, you can further do the selection part of which method to use. But for our purpose, which is to getting started with the Matlab and to use this Matlab tool, various inbuilt packages, to solve our chemical engineering problem, we can start with a basic solver, right? So that's why we are selecting the ODE 45 as a basic solver and starting with this solution. Okay, so what we have done so far, we have understood the problem. Okay, we identified the equation involved in the problem, and then now we know what numerical method to use to find the solution. Okay, now what we will do, we will try to code this and simulate this problem in Matlab. So let's start with that. I'm creating a new live script. So here we will start clear all the previous variables, close all. So clear all will clear the previous variable, CLC will remove the clear the command window, and then close all will remove the various plots if already it will close all the plots, right? Okay, now here, so this is our start of code. Now we have to do code in three parts. First is we have to first find the basic solution and then move forward with the other sensitivity and optimization part, right? So we learned previously that in Matlab, if you provide one percentage symbol, that means it's a comment. But if you provide 2% symbol, you can see that appears this blue line. Okay, so providing two comment symbols or 2% symbols, that means you are creating a section within the code. Now this is useful when we have a long code. Then in that case, it's better to run the code in very small parts, right? So if you will see in the live editor script, you can see run section option. Okay, with this run section option, so let's say you have done some coding part here, and then again you define this part. So line 5 to 6 becomes one section of your code, then line 7 to 8 becomes another section of your code. So you can run this code in a parts. You can see line 5 and 6 is my one section, and if I run this particular section, okay, only line 5 and 6 will be run, nothing else, right? So this is how also you can work with the long script. This is useful particularly to debug your long to debug any longer code. Okay, so not problem 1, this is part 1. Okay, part 1 is a basic solution. Okay, now what we will do, we will first define all the global variables that we have in this problem. Okay, and then we will give them corresponding values. So for that, we know we have to use global command. Okay, so global command, and then what are the variables that we have? You have concentration, temperature, volumetric flow rate, right? So let's input all. So first we have CA0, you have T0, you have V total volume of your reactor, then you have volumetric flow rate. Okay, you have activation energy, you have also heat of reaction, right? So heat of reaction, you have activation energy, pre-exponential factor, what else, heat capacity, density, gas constant. Okay, so heat capacity Cp, density, gas constant R. Oh sorry, you don't have to put comma. When you are defining the global variable, they are separated by space. Okay, anything else that is left? Let's look again. We define CA0, T0, volumetric flow rate, total volume, activation energy, pre-exponential factor is also defined, Cp, density, R. Okay, what else? Heat of reaction is defined. Yeah, so all the variables are defined. Like these are the global variables that we have to use. Now, so you can comment this also, like providing or providing global variables. Okay, now let's provide the value of each of this variable. So you have first CA0. CA0 is given as 2 mole per liter, 2 mole per liter. Okay, comment this part. Okay, then T0 is given as 300 Kelvin, which is inlet temperature. Sorry, percentage K. Then you have total volume of reactor, which is given as 500 liter. Then volumetric flow rate, V0 is given as 0.5 liter per minute, right? Sorry, it's 0.1. Okay, 0.1. You have your heat of reaction, H reaction, which was given as minus 50 kilojoule per mole. So I'm converting it into joule per mole. So minus 50,000, okay, 50,000 joule per mole. Activation energy will be, this is also 50 kilojoule per mole, so 50,000 joule per mole. K naught value, which is pre-exponential factor, is 2000 liter per mole minute. 2000 liter per mole minute. Cp is given as 4.2 joule per gram Kelvin, right? Yes, joule per gram Kelvin. Now since it's a command, it won't be considered in the code, but it's always a good idea if you are dealing with various units to write a comment denoting the units, right? So if there is an issue in a code, you know, if you can make sure that if there are issue in the unit conversion or not. Okay, so this is gram per cc, gram per liter, 1000 gram per liter. And lastly we have gas constant, which is joule per mole Kelvin. Joule per mole Kelvin. So these are my global variables has been defined here. Now what I have to do, I have been asked write a code which finds the change in the concentration and temperature conversion also with respect to variation in the volume. So what I will do, I will create a V span which will change the volume of reactor from V0 to V total, right? So I'm providing two limits for on my volume part. Okay, so lower limit is 0, which will be the inlet point. Okay, so if you are considering the change with respect to if you are considering the concentration change with respect to the length of the reactor, so starting point is L equal to 0. For L equal to 0, your volume is 0. For L is equal to Lz, your volume will be total volume. So you have to see the concentration profile in between these 2 points, right? So we are providing that my lower limit is 0, my upper limit is total volume, which is the maximum volume. What will be the change in this 2 part? Okay, now we also know the initial concentration. So initial concentration, I am defining it as Y0. Y0 is combination of Ca0 and comma your T0. Okay, so this is my initial concentration, Ca0, Ta0. Okay, now in ODE 45, help ODE 45, what you need is you need your ordinary differential equation, you need the span over which you want to integrate. So we provided my volume V0 to V total, you need the initial condition. Now you have to define a function which represents your ordinary differential equation. So for that, what we will do, we will create one more function file which represents the ordinary differential equation ODE of PFR. Okay, so this is my function. Right. Now the input to this function, so input to this will be my initial concentration, so my Y0 value will be the input. Okay, Y0 so here ODE PFR, let me just see briefly. Function, your one input is V and another input is Y. So here my y variable contains concentration and T0 value, right? So if I look at here, let me just see whether I created a column. It's a row matrix. So first, taking values from user. Before that, all the global variables that we have defined in our main function, we also have to provide it here, so that we don't have to put a value of this variables in my function file also. Okay, so here also I have defined the global variables. So this will call the values of this global variable from the main script and provide it into the function file, so I don't have to redefine them in the function file, right? Now what I need in this ordinary differential equation here is, my first equation is minus k Ca square by V0, okay, where k is k0 exponential minus e by rt. Okay, my second equation is minus h heat of reaction into r divided by rho Cp V0. Okay, right. So first what we will do, we will find the value of k and rate of reaction, and then find the equation 1 and equation 2. So for that I need a variable, right? So my vector y, where I am defining c and 0, it will be considered as an input. So first variable here is concentration and second variable is temperature. Okay, so yeah, y2 I am calling them, okay, taking value from users, finding the value of k. Okay, your k is equal to, we have k0 into exponential minus Ea by RT, right? Okay, so you are finding the k, then finding the rate. So rate is equal to k into Ca square, right? So this becomes my rate. Now change in dC A by dy, or dC by dy, you can write it anyway. So change in the concentration with respect to with respect to volume is minus k Ca square by b. So minus k Ca square is your rate divided by volumetric flow rate, right? So here I can put dC by dV, let's say I call it in this fashion, minus rate divided by V naught, right? So this becomes my first ODE. Then change in dt with respect to volume is equal to, you have minus heat of reaction into rate divided by rho Cp V0. So minus heat of reaction into rate divided by density into Cp into not V total but V0, right? V0. Now let me put it this as what I'm calling it here, dy by dv. Okay, yeah, dy by dv is equal to ordinary differential equation, which is function of y, and dy by dv 1 is equal to dc by dv. This is my first equation. dy by dv. My second equation is change in dt with respect to volume, right? So this is what I have created in my function file. Let me just verify it. We have compute concentration, temperature, R. Then you find mass balance equation, I R by V0, and this. Yeah. We don't need V here actually. Anyway, doesn't. We don't have to. So this is my function. I have defined ordinary differential equations through this function. I know T span, I know Y0, so that I can use the OD45 to solve this problem or to solve this issue, right? Now, calling ODE 45 function to find the value of CA and T for various values of volume, which is V. So I will create V by variable is equal to ODE 45, which is a function of V and Y. My function is ODE for PFR, right? My span over which I want to do integration is given in the V span, and this is Y0, right? So till this point I'm working. Let's verify whether we are doing it correct or not. So I will run this code and see if I'm getting any error. Yeah, I'm getting an error which is invalid expression when calling a function or indexing variable, use parenthesis. ODE, what happened? ODE 45 @VY. Yeah, here I have to call the function by providing the value of y also. Okay, now let me see. Again, oh yeah, there is no space here, sorry. So it's a function of v and y, and this is how you call it. Now I'm getting an error. That error using ODE argument, ODEY must return a column vector. Line 28. Let's look for the OD45 again. I know what exact error it is, but let's try to identify together. So while providing OD45, you provide function of t and y 2t and t, y, a and b. T-span. Probably this. must return a column vector. Yeah. Maybe this way I have not defined it correctly. Let me see. ODE PFR y0. But it's asking me for a column vector, so I have to define it in a different way. Now same thing. Yeah, now it's a column vector, so this should work now. Let's run it. So it has run it, and then you can see I have different values of y, which contains concentration and temperature, various values of v. So from 0 to 5000, 0 was our initial value, 5000 is the end value. So it has taken the increment in between, and for each increment, value of concentration and the temperature is given. It's find it, right? So this ODE function that we provided is working correctly as of now, right? Now what I can do is, since I know the value, what I will do, we will create a file which stores this value. So storing this data, right? For that, I know the volume is saved in V. My Y column contains concentration as well as temperature. So my Y matrix, first column of Y matrix is concentration, second column is temperature. So I will store it in here, that all row first column is Ca, temperature is Y, all row second column. We have been also asked to find the concentration, sorry, not concentration, conversion XA with the variation in the reactor volume. Now conversion is given as Ca minus Ca0, sorry, Ca0 minus Ca0 divided by Ca0, right? So you have Ca0 minus Ca delta Ca divided by Ca0. Okay, so this is a change in the conversion, right? Now for storing this data, I will create one file which is, I am saving it as part 1. This file is for writing. Okay, F open, then yeah, I will give them file name as F1, which will open the file. F printf, it will take the F1 and print. First we have to provide the value what we are going to do. So we are printing the volume, which is in liter, then slash tab, I have volume in liter, then you can provide temperature, which is in Kelvin, Ca mole per liter slash T, then K your XA. Okay, XA doesn't have any units, so it's fine, then N. Now what I can do, I can run a one loop for I is equal to 1 to, let's say, length of Ca what I will do, I will open this file and print volume value %f/t %f/tab %f/tab again %f/tab/n. So first I will plot corresponding value of volume, then corresponding value of temperature, corresponding value of concentration, corresponding conversion, and this is the loop. Like, so till now we have run the code. Let's run it and see. Oh sorry, I printed on the script. I meant we wanted to print in the file. Okay, so this is how it will look like. So with change in the volume, this is how temperature is changing, this is what concentration is, and corresponding conversion. Let me put here, I want to print everything in file, not on the command prompt. Okay, and here at all place I forgot to suppress the output. So it has run the code. Answer 48. Again, suppress the output. Code has run. You can see part 1 file has been created, and in which all the data is tabulated. Right? So this is part 1. We can also do the plotting of this part. I can visualize how this concentration and temperature is changing with the volume through plot. So for that, let's create one figure. Now what I will do, all these 3 figures we will try to put it in one plot. All these 3 figures we will try to put it in one plot. So first row of this plot will contain change in the concentration with respect to volume. Second will contain change in the conversion with respect to volume, and third will be third row will be change in the temperature with respect to volume. Right? So all these 3 plot in a same diagram. So for that we will use the subplot command. In the subplot command you have to say, so mn becomes your number of rows, number of columns, and out of which part you want to access. Right? So I am doing subplot 311. That means I want to create a 3 plots in a row, out of which I will access the first row. Okay, then let's plot our volume. So x value is V. Concentration, let me provide it as a red. So minus this represents red color. You can also provide line width, right? Let's say line width 3. I think this is enough. You can also provide, if you want in between points, you can do R star. Provide X label. X label will say volume in liter, right? Y label will say CA, which is mole per liter. Now I want when provide the title, which is says change in concentration, change in CA with respect to reactor volume. Okay, and I can do grid on. Similarly, what we will do, we will provide subplot 2 and 3, subplot 2 will include conversion XA, then last third is the temperature part. And run the code. 3 2 oh sorry 3 2 1 and this is 3. So you can see we are getting this plot. Now as my volume is increasing, concentration is changing, it's decreasing. Here with respect to increase in volume, my conversion is going up, right? And as volume is increasing, since it's an exothermic reaction, temperature inside the reactor is increasing because of the exothermicity of the reaction, and it's an adiabatic reactor, so there is no heat exchange, right? So you can see your temperature is also increasing. So this is how the variation is occurring. Now here we haven't provided a number of data points. So by default, OD45 has selected 40 data set between 0 and 5000, 0 and 5000, which were the two extreme limits for our integration, right? If you want, you can provide the in between limit also, like if you can decide in how many number of steps you want to go. So let's say I provide V is equal to, at every 50 I want to do this calculation. So you can see my number of data points has increased. You can see my XA has doubled. So from 41 it went to 101 data points, right? And you get this much in between data points. This dot representation doesn't look good, so let's get rid of this. And probably these are too many data points, so I will stick to the default value for as of now, since I don't have any specific need. Okay, so this is how my plot looks like. So this was the part 1. We did the basic analysis, that how with the change in the volume, what will be the change in the concentration or the conversion. Okay, so you can see when we reach the end of our reactor, my conversion of A is somewhere around 0.34, which is actually very less. So in that case you can change the design of your reactor, maybe try to increase the cross sectional area to increase the volume, or you can go for much longer volume, for much larger volume. So let's say if you want to keep the cross-sectional area constant, then you can increase the length of your reactor, which will eventually increase the volume, right? So this concludes the part 1. Now what does part 2 say? We have to do sensitivity analysis, where we have to first look at the feed concentration effect, where you have been asked, like, if feed concentration is between 1 and 3, so various values of feed concentration if you have, plot of how it will affect the conversion and outlet temperature, right? So let's do the part 2. I'm defining it section 2, part 2, which says sensitivity analysis. Okay, you have been given 2.1 says effect of CA0 on output, right? We have been provided CA0 range, so it starts from 1.5 to 2.53, right? So I can just create 1.5 to 3. So this is my range of CA0. Now here in the previous part, in the part 1, CA0 was constant, okay, and we were just solving ODE for various values of y, okay. Now here our CA is also changing, so what we will do, we will run a loop for various values of CA0, which will run over the CA0 range. Every time we will update the value of CA0, which will be then put into the OD45, okay. This is the basic idea. So for that, what we will do, we will create one I loop for I ranging from 1 to length of CA0 range, and what we will do, we will update the CA0 value, CA0. So I am updating the CA0 value. Mind you, CA0 is a global variable, right? So I am updating it, and that will become CA0 underscore range of I. So CA0 will take the CA0 range value. It will update the value. Now I can call the OD like I did in the previous part. So V is equal to Y, so V volume and your solution is equal to OD45. Your OD PFR is provided, then you have Y's volume span is also given from 0 to your final value, and Y0. Now Y0 value I have to update again. Previously Y0 was created as CA0 T0. This has been created, but now I have to update it again. So Y0 will be updated here. So it will take the new CA0 value, T0 value, and we will then we will solve the OD. Right? Now this has been solved, but here in the part 1, what we did, if you see that figure, let me run this. In this figure, from 0 to 5000, we do the integration over step by step, and then find the value in between value, right? But now in this case, what we are interested is in the final concentration. What will be the value at the final, at the outlet, okay, CA0 at the outlet and temperature at the outlet, right? So I am only interested in the final value. So if you will see here in the y column, which is the output of my ODE function, I am only interested in the end function part, right? This two value. So I should collect this data only and not the other data, okay? So for that, what we will do, we will create a function CA0 effect. This is nothing but, so I will create a zeros size CA0 range. So here what I am doing, I am first accessing the size of CA0. Size of CA0, this thing, CA0 range size I am collecting, and if I do the zeros of this size CA0 range, this will create the 5 cross 5 matrix. So for each value of Ca0, it will create corresponding final Ca concentration data matrix, right? Similarly, I will create the temperature data matrix, which I will call T Ca0 effect. Okay. Now, once I have done the ODE, I will update this value by, so from Y data, I want to only call the final values for concentration. So if we will do Y and 1, what we will do, it will take the last row and the first column, so which corresponds to the final entry point, which is at V total, right? Similarly, TCA0 effect, I will become Y and data point 2. Once this is done, now I can plot this data again. So similar to the previous part, let's create a figure. This time I will create a 2 side-by-side figure. You have Ca0 range as a x-axis, you have Ca underscore Ca0 effect, right? Mole per liter. Actually, we have been asked to compute conversion, right? So maybe I can update it here. Let's say XC0 effect. C0 minus so I'm also finding the conversion also, because we have to plot the conversion. XC change in XA with respect to CA0. See, I'm providing this, I'm doing C underscore A underscore 0. So what it will do, it will write A and 0 as a subscript. So when I will do the plotting part, you will see how it is written. Okay. So this is plot 1. Let me do plot 2. 1, 2. This is temperature. Now I am only interested in part 2. Part 1 I have already seen, so I will do the section run part, or run section only, and see how my plot looks like. 1, 2, 1. It has not updated first. Oh, my mistake. I have to remove this. These are same plot. So you can see this is how it changes. So if I increase the concentration, inlet concentration of my reactant A, the conversion is increasing for the same volume of a reactor, right? At the same time, its conversion is increasing, outlet exothermicity, because of the exothermicity of the reaction, outlet temperature will also increase. That's why you can see the shoot up in the temperature value here. Now let me put in between data points here. So let's highlight them by star. Let's keep line width 2, 2, run this section. Yeah, this is how it looks like. Okay, so right now we have been provided with only 5 in between points. So this is how it looks. You can do fine tuning. In that case your curve might become much smoother also, right? So let's say instead of 3 I can go till 5 concentration also, and here my this is how my profile looks like. Okay, so at one point it will become saturated, you can see. So let's say instead of 5 let's do 10 and see what happens. So after my initial concentration is somewhere around 7 mole per liter, you can see there is very little effect on the concentration, because you are getting almost complete conversion for a given reactor parameter. But in that case your temperature is increasing very rapidly and linearly, right? So for the initial lower concentration part, in this zone you can see with increase in temperature, with increase in the initial concentration, your temperature is increasing, but not it's gradual. So in this part slope is less, but here after your 5 mole per liter you have a constant higher slope. That means here your temperature will shoot much faster. Okay, now this is also an important aspect, because you are limited when you are designing an equipment. You are limited by its properties, its material of construction property, right? So you have to see up to what temperature you can do. You have to work with safety limit also. So in that case you have to find some in between point, which is actually the part 3, where you have to find the maximum conversion up to a certain temperature. Like your reactor temperature should not cross beyond this. Okay, we will come to that also. Here I was mentioning this part that I have written C_A_0. So this will put your data into the subscript, right? All the text into the subscript. Okay, so just a small anecdote. Now here I'm visualizing this effect individually. So like it's change in the concentration, I'm seeing it here. Now the second part has been asked, which has been asked in the part 2, is also study the effect of inlet temperature and how it will affect the conversion and the outlet temperature. Do we have anyone? No. Okay. So again, similar to the previous part, what we will do here, we will create matrix for various temperature value. I am simply copy pasting it. So effect of, this is 2.2, this becomes effect of T0, which is inlet temperature on output. I will have a T0 range. What range we have been given? 300 to 340 Kelvin. So for that 300, increment of 10, and 340 Kelvin, right? C0, CA, temperature effect, so I will call it as T0 effect. This is T0 range. So previously what we did, previously our global variable, which was input concentration of the reactant, changed. Now variable T0 is changing, so I am creating a matrix which will note the changes in the concentration and temperature with respect to T0, right? So we will run a loop over the length of T0 range. What we will update, so previously we updated C0 since CA0 was changing. Now we will update T0 value. T0 is global variable, right? So we will update the value of T0, saying that length of T0 range I. Update the value of Y0 for the corresponding T0. Solve the ODE, same problem. Now only the value updatation will slightly change. Okay. So exactly the same code, only some part changes, right? So previously we changed here in the 2.1, we changed the CA0, updated the Y0, solved the ODE and took the final data of concentration and temperature. Now instead of CA0 we are changing the T0, updating the Y0, solving an ODE and then getting the concentration and temperature data, right? So once this is done, you can plot this as T0 range XA, T0 effect, so let's run this section and see. Yeah, so this is how it looks like. If you increase the inlet temperature, you notice that your conversion is increasing much faster. Okay. Okay. Why we have a higher conversion? Oh yeah, sorry. So here what has happened that our previous CA0 concentration, which we changed till 10, has been kept still, and that's why since it's a global variable, uh, we are working with higher concentration, so you already see a higher conversion. So what I will do, instead of changing global variable, let's only change the Y0 so that we don't have to worry about changing the global variable elsewhere, right? So I'm just not updating CA0, but I'm just updating Y0. I think that is a better way, because I don't have to worry about global variable changing and then trying to think why something went wrong. Okay, now let's run the entire code, because so this is how it looks like. For a given reaction parameter, if you are operating at 300 Kelvin, your final conversion will be 0.34604, right? So this is what we saw in the initial plot part 1, that when we are operating at 300 Kelvin and when we reach the final part, our conversion is this much, 0.34346, right? So similarly, for a given data at 300 Kelvin, we start with this conversion. But if I increase the inlet temperature, you can see my conversion is increasing drastically. Okay, so from 300 to 310, my conversion has increased to from 0.36 to 0.54, right? Similarly, obviously outlet temperature will increase if the conversion is increasing. Now you can compare these two things side by side. So for your plot 1, here what is happening with when you have a lower concentration. Why this plot is looking like this? CA0 0.3, just a minute, right? Have we updated anything? Doesn't seem to have changed anything. I'm not sure about this decrease. Let me just quickly check my previous code and see. Yeah, from 1 to 3 it's only increasing. One, two, three, it's only increasing, and then yeah, this is how it should look like. There should be no dip in between. So probably we made some mistake here. Yeah, this is some mistake here. I'm not sure what happened. Two point one y span y0 is CA0 range I, and T0 is global variable, we are not changing it. Oh yeah, here my mistake is here, that since we are changing CA0, so the conversion, actually it was calculated based on the global value, that's why it was going down, but it should be the current new CA0, right? So this is how it is, and yeah, now I think it will work fine. Okay, let's run it. So this is my one figure, this is my second figure. So you can see here, you can do some sensitivity analysis also, like from 300, if you increase the temperature by 40 degrees centigrade, your conversion is increasing very drastically, while for initial part, increasing your concentration from 1 mole fraction to 5 mole fraction also leads to a higher increase, but after 5 mole per liter, increasing concentration, initial concentration has not much effect, right? Now these are two different plots, one is with respect to temperature, one is with respect to initial concentration, so sometimes it's difficult to visualize. In that case, what we can do is we can create a 3D plot of the same data, where we have Z value representing the temperature or outlet concentration, and X and Y represents the input concentration and input temperature value of the feed, right? So for that, I have to create one 2D matrix where I have the data for both change in the temperature as well as the initial concentration part. Okay, so again we can modify this. This has been not asked in the question here, but let's try to do that, because yeah, because it will help you to better visualize your data. So what I will do, we will put section 2.3 here, which says it's like 3D visualization, sorry, visualization. So I have temperature range, we also have a CA0 range, right? Now previously when I was only varying one variable, be it be CA0 or TA0, I had to create only one directional matrix for CA and outlet temperature, right? But now since I am varying both, I will need a 2D matrix to represent CA and XA. So for that, let's create a zero matrix, which is a 2D matrix with both length and size, length represented as CA's concentration change and the column being represented as the temperature change. Okay. CA naught length T naught range. So basically what it is doing here is, if I paste on the command prompt, this is creating a 0 by 0 matrix where each row represents the variation in the concentration while each column represents the variation in the temperature. So at any point at any selected row and column, we will have both variation in temperature as well as the concentration, right? So you can see my CA0 range, it's varying from 0.5 to 10 as of now, and the temperature is from 300 to 340. So 300, 310, 20, 30 and 40 Kelvin. Right? So this is how this matrix is created. You can name this as CA 3D effect. I'm just writing 3D matrix, or okay, because although it's a two-dimensional matrix, but at the end we will visualize the plot in the 3D, so I'm writing it as a 3D. Now as I said previously also, that naming of your variable becomes an important part. Since I'm okay with this naming, it's fine. You can use more meaningful name, like previously we named as temperature TO effect, temperature CA0 effect, right? So you can name it in a better fashion. Now what we will do, we will vary both CA0 and temperature. So for that I will have nested loop of CA0 and T. So here what I am doing right now, let me just show you 1 minute. Yeah. So we are varying CA0 first. So for first value of CA0, now what I will do, I will have another for loop which varies all the T0 value. So I am first selecting one concentration, and for that particular concentration I am varying all the temperature data. Okay, and for that combination, so basically I am selecting one concentration here and then I am changing all the temperature. For all this we will find the corresponding final concentration, corresponding temperature, and store it. Then I will move forward with the second value. For that second concentration, look at all temperature data and find the solve the ODE, find the final concentration and the temperature and update it, right? So for that, now my Y0 becomes, so Y0 includes concentration which is taken from I loop, while temperature value is taken from J loop, right? So for concentration I have I loop, so Ca0 and my indice is I, while for temperature my indice is for going J, right? You solve the ODE, same, your only Y0 value changes here. Then you update your 2D matrix I comma J, I comma J, right, T underscore 3D I comma J, and this will become right. So you have XA this is updating concentration, this is updating temperature, and then I am finding corresponding conversion, ending it. So if you will run this part, let's run this section only. If you will see my temperature 3D, this contains data. So the row sorry, first column will correspond to for one temperature change in the concentration, row will correspond to for one concentration change in the temperature, right? Now I have this data, but how to visualize it? So for plotting you have various options in Matlab, but now I want to do the 3D plot, right? So let's see what 3D plot option I have and what option will be the best to represent a current scenario. So there are 3D plot. So let's look at creating 3D plots example. So one, you have line plot, which is represented by plot 3, where you provide XYZ data and it creates this line plot. Okay, this is one option, but my data is slightly different, so I want to represent it in a better way. You have a scatter plot also. Yeah, so this is something we might can think about, that our z-axis becomes final conversion or temperature, x and y axis becomes Ca0 and T0. This is one option. You can also provide the heat map data. You can also look for surface plot or contour plots, which I generally prefer. It's not showing here, so let's look at the surf plot, right? Yeah, so something like this might work. So surface plot, we have to provide three data, x, y and z, where x and y are your x and y scales and z is your 2D matrix, which includes the corresponding data, right? So it's a three-dimensional surface plot. Your z matrix is kind of a 2D mesh data. Okay, so z is a 2D matrix here, right? So this might work better in our scenario. Okay, and you can see you will be able to see at what point your concentration is increasing, at what point your concentration is decreasing, and so on, right? So let's try to plot a surface plot. So for that, once we have this data ready, let's create a figure. Let me do surf. We will have my x-axis is Ca0 range, y-axis is T0 range, z is XA3D, right? Then I can copy paste this label. X label becomes Ca0 mole per liter, Y label becomes T0. I can provide Z label, which will be referred as XA. Okay, conversion. Title will be change in XA with respect to CA naught and T naught. Right. So this is one plot. I can also see the change in temperature. Change in temperature with respect to C0. Let's run this. I think we have encountered some error. Yeah. Data dimension must agree. So there is some dimensionality error. CA0 is 19 cross 5. T is 19 cross 5. Why it's not? It should work, right? Just a minute. What happened? X3D IJ. Y and 2. Length CA0, length T0. Dimensionality is matching, right? Still getting some error. Let me see. If I do directly surf XA 3D, yeah, this is how it looks like. Just a minute. So plot is working, but there is some dimensional error. Let me check. Five cross 5, 4 cross. Let's do help surf. It's working fine. I don't know what's the issue here. Data dimension must agree. Although dimensions are matching, CA 3D, T 3D, XA 3D is also matching. T range is there, it's 1 cross 5. CA0 range is 19 cross 5. I'm not sure why this error is coming, although the plot is correct. So this is how it looks like. If I look at the temperature, surf T3D, this is how temperature profile will look like. Here x and y axis are not labeled correctly, so that's why you cannot see. But for the lower value of inlet temperature and lower concentration, your output temperature will be low. If both are high, then your output temperature will be much higher, right? So this is how it looks like. Similarly for concentration also, if you will do XA3D, yeah, this is how it will look like. So initially this kind of increase you will note with respect to concentration, and with respect to temperature, obviously you know the previous part. So this is how the increase will look like. Okay, so this is kind of a 3D representation which shows that which part it's more sensitive to. It's more sensitive to actually concentration. So if you will recall, the concentration profile was looking like this. Compared to that temperature profile, it had a constant increase, right? Here I think there is some syntax issue, or where it's not matching the dimension. All the dimensions are correct. Let me try with a lower dimension first. Yeah, now it's matching. Okay, so yeah, probably the serve command requires a square matrix. Yeah, let me see here. Okay. Sin x by x. Okay, the issue is that previously when I had selected this, if I do the increment in 5 steps, so when my 3D matrix, when my 2D matrix is 5 cross 5, so corresponding change in the CA0 and X is T0 is also 5 cross 5. So if I want to write this command, I want to plot with respect to both X and Y data provided. In that case, my 3D matrix Z matrix should be a square matrix, else it won't work. So that's the limitation. So maybe I can change from 3, let's say 5. So this will change in the increment of 5. So you have 3, 5 by 0.5, and then T0 you can change with respect to 5 and see. Not 55. This way probably it works. So it requires both both the matrix data to match. So CA0 increment and T0 increment should match. So this is how your concentration change will look like with respect to T0 and C0. If you increase the more data point, then you will get much smoother curve, right? So previous one was the temperature, this is CA0. So CA0 is more sensitive to your concentration. So as you can see, with change in the concentration, it's increasing more, while the temperature dependence is slightly less. Okay, so this is how you can visualize your data in 3D matrices also. Now let's go to the final part. Anyway, we are close to the closing the session. It's already 2 hours. So final part, it says that we have to find the optimal condition, determine the inlet temperature which maximizes the conversion while keeping the outlet temperature below 350 Kelvin. So there are some safety constraints that outlet temperature should not increase 350, and for that we have to find what maximum conversion we can go till temperature reaches 350. Okay, so in the sensitivity analysis part, if I run it again, we were looking at this plot which change in the inlet temperature, determine the inlet temperature which maximizes the conversion while outlet temperature does not go to 350, right? So here this is the outlet temperature, this is the inlet temperature. So for outlet temperature to not go to 350, it touches 350 value when my inlet temperature is 330 Kelvin, right? And corresponding to that, corresponding to 330, I can see I have a conversion of 0.84, below which my conversion is less. So from this plot itself I can see that my temperature should be less than around 329, right? Okay, let's say somewhere around 329 or 328, where I am just touching the limit of 350 for the safety limit, and I have a maximum conversion, right? If there was some up down pattern, then in that case I have to determine what exactly that point is. But from here I can graphically also determine that let's say somewhere around 328 or 329, my data point will correspond to maximum value. My conversion will be maximum while the temperature limit is 350. Okay, so this is from graph, but let's say if you want to deduce it from code itself, you want the exact value, what exact value of temperature you want. So for that you can do further calculation, part 3, which is finding optimal point. So for that, what I will do, since we are out of time, I will call the data from my previous point, and okay, I'm just copy pasting the snippet and I will explain it to you then, since it's a very fairly small part, right? So what I'm doing, I'm creating a test metric for the inlet temperature which goes from 300 to 340, since we know that I closed that plot, but in between that range we know this crosses a 350. In between this temperature range, my outlet temperature crosses a 350, right? Now I am increasing the increment. Previously I was increasing the temperature increment in the 10 Kelvin, but right now I will increase temperature in increment of 1 Kelvin to find the data. Now I am creating X optimal condition, which is a random zero matrix of corresponding T0 test size, corresponding output temperature also I am computing. Okay, so I am creating two matrix. Now what we will do, for each of this temperature range we will find what is the final what is the final concentration and what is the final temperature. Okay, so here I have found the final conversion and final temperature. So this is nothing but your 2.2 part, right? So in 2.2 we varied the temperature and find out the corresponding final concentration and temperature. So same thing, but you are increasing temperature in 1 Kelvin increment. Okay, once you have this data ready, I am creating this logic matrix which says valid ID uh, if T out operating temperature is less than 350. Okay, so what this will do, for that, let me run this code first and I will show you. Oh yeah, ODPFR. I have to change the name. ODPFR. What happened? Now it's working. It has already given me the output data. So at in optimal inlet temperature of 329 Kelvin, you will get the maximum conversion, and your corresponding outlet temperature is 348, which is less than the safety limit. But for that, what logic I have used is, first I am creating this valid ID index. What it will do, for my all the output optimum output operating temperature that I have computed between for various values of inlet temperature, I will get the corresponding valid index. If the temperature output temperature is less than 350, I will get logic as 1, else 0. Once I know this logic, like from column 1 to, I think this is 20, 1 2 3 4 5 6 7 8 9 10 11, so column 30, I know the temperature is less, output temperature is less than 350. Above this, output temperature is higher, so I will avoid that. Now for any correct logic, any temperature which is less than this, I will find the maximum temperature out of this operating value, which is computed from this max command. So I'm finding the maximum value and finding corresponding ID. So optimum temperature will be that corresponding valid ID's temperature, which is optimum input temperature T0. Okay, and then I'm just printing it, right? If this condition does not satisfy, if I don't get any valid ID which is less than 350, then you display that there is no correct solution, right? So this is how you can run overall code and then find out what is the maximum uh, working inlet temperature which you can use, which does not violate your outlet temperature requirement, okay, or the safety requirement of your reactor. So this was the overall example which I wanted to give for plug flow reactor. Now uh, there were this problem designed for today's class, where we were supposed to solve various fsol and f0 f VPA solve examples, but let's put it into the next class. I will still upload this. If you want to solve it, you can do it, or else what we will do, we will try to solve some of this problem in the next class, depending upon what kind of content we have in the next class. So if we have a new content, we will follow that, or else we might solve this some problem from this class and then move ahead with the next content. Okay.